we looked at the behavior of a mass hanging from a spring when there wasn't any gravity, but it's kind of hard to get that kind of situation because you have to go out into outer space somewhere. Here near the surface of the Earth, there is pretty appreciable gravity. So let's see what happens when we add gravity to the situation. Now, the title kind of spoils the surprise. It turns out that gravity doesn't really change the behavior of this situation. We get the same similar differential equation, but it's worth looking at why that's the case. So let's suppose that we have a mass that's m kilograms and hanging from a spring that has spring constant k, so it's k newtons per meter, and we have some gravity. So acceleration due to gravity is g meters per second squared. So near the surface of the Earth, this is about 9.8 meters per second squared. Okay, so let's see how gravity changes the situation. So we have a spring here and a mass, and let's call the natural, let's say that, right, when we first looked at the situation with the spring, we said that y equals 0 is at the natural length of the spring. Well, in the presence of gravity, this spring is, because we're hanging a mass from the spring is going to stretch a little bit when the mass is hanging motionless. So, and let's call this distance that it stretches, let's call that distance L, I guess. Now, in this situation where the mass isn't moving, we can use Newton's second law to figure out something about L. So this is the equilibrium situation. So in the equilibrium situation, right, we have Newton's second law, which says the net force is mass times acceleration, and acceleration is y double prime. Well, in the equilibrium situation, there is no acceleration because the mass is hanging motionless. So the right-hand side is 0. The left-hand side is the force due to the spring, which as usual is minus k times y, plus the force due to gravity. And gravity is, well, it always acts in the negative y direction, and it's mass times g. Okay. Oh, and actually I've made a mistake here. In this equilibrium situation, y is L, negative L, right? Because the mass is hanging distance L below the natural length of the spring. So putting negative L in here for y, we get k times L equals m times g, and this lets us find L. So the distance that the mass stretches the spring due to gravity is m times g over k. Okay, fair enough, but this, all of this calculation, this was in the equilibrium situation. So what can we do to get back to our differential equation? So for the full differential equation, we have to remove the assumption that we're in the equilibrium situation. So what we'll do is, right, things seem complicated at first because of this extra force. But what we can do is, right, the full differential equation is minus k times y minus m times g equals m times y double prime. Okay, so it seems like everything is going to be a lot more complicated because now we have this extra term in our differential equation. But there's a clever way to remove this complication. If you think about a mass hanging from a spring in the presence of gravity, right? It seems as if the equilibrium position is the natural length of the spring. So what we're going to do is call this position 0, we can't call it y equals 0 because y already means the natural length of this unstretched length of the spring. So we have to pick a new variable, call this u. So you can see here on this diagram, u is just like y, except it's lower. So let's see. When u is 0, y is negative L. So that means u is y plus L. Right, so if we plug in negative L for y, which is this equilibrium position, then u is 0. So let's use this new coordinate function u. Let's do a substitution to see what this differential equation turns into. So let's take a derivative. So u prime is y prime plus, well, L is a constant. So when we take a derivative, L goes away. U double prime is y double prime. And now we can do the substitution in this differential equation. We get minus k times y, but right, we can solve this equation for y. Y is u minus L. So k times u minus L minus mg equals m times y double prime, but y double prime is the same thing as u double prime. Okay? So we get minus ku plus kl minus mg equals m times u double prime. And so here's where the magic happens. KL minus mg, if you go back up to here, KL minus mg is 0. So we just get minus ku equals m times u double prime. So this differential equation that we got for u, this is exactly like the differential equation we got with y's in it in outer space where there was no gravity. So we see that this mass and spring will behave exactly the same in a gravitational field as it does outside of a gravitational field. So usually when we write down the differential equation, this differential equation for a mass hanging from a spring, we just ignore whether there's gravity or not because it doesn't actually change the behavior of the system as long as you use, as long as you label the equilibrium position of the mass with position 0, whether you call it u or y. As long as you call that position 0, you get the same differential equation.